Next up and last for this session before the coffee break, we've got Dr. René Heller. He's an expert in extrasolar planets at the Max Planck Society in Germany and an awarded lecturer for astrophysics at the University of Göttingen. A former postdoc at McMaster's Origins Institute, his recent research on interstellar photon sails was invited as a plenum talk at Breakthrough Discuss in 2017 at Stanford. His talk here today is entitled Maneuvering Interstellar Light Sails. Thank you very much, René.
Thanks. I want to start off by thanking the IRG and IAA for having me. It's a real pleasure and honor to be here and join this community. And also thanks to Andrew and your group for having us. It's a real pleasure. My talk is about the possibility of using light, and light here meaning photons, but also a little bit of mass, light sails, to maneuver to other stars. So it's, I think, a good fit for the conference topic, in the light of other stars. So a little bit about my background. I'm a team lead for the Plato mission of ESA. I work in Germany at the Max Planck Institute for Solar System Research, and I do have a background in astrophysics, which is why I also would like to be inclusive and diverse, so to say, and give you a few equations, if you don't mind. But we'll step through them step by step, so they won't hurt, I guess. Here's a little animation of what a flyby around or by a potential planet around a nearby star could look like. And in particular, that's an animation relating to Alpha Centauri, capital C, little letter B, that is Proxima Centauri b. Excluding relativistic effects, by the way. In reality, if we would approach that planet, we should start seeing the backside of the planet because the light would bend. But anyways, that's just an appetizer. So we've heard some opinions here about how realistic interstellar travel could be in the next decades, centuries, or even millennia. And as a scientist, I like opinions, but what I like more are numbers. So I went into the literature and looked up a couple of top speed records that humanity has achieved in the past. So here's a little graph that I published in 2017 in the monthly notices of the Royal Astronomical Society. And let's see what we see here. We see, here's a cursor, yep. On the y-axis, we see the speed top record at the time in units of the speed of light. And here's time and the respective year. So we are somewhere over here. Encoded in red with crosses here, that's trains. And I start out with a train here, and I'll show you in a second what this actually refers to. So here's a couple of top speed records in the 19th century of trains. Somewhere here is the German ICE and the French TGV, and this could be, I guess, the Chinese Transrapid. Then in green we have cars, with planes in blue, and finally we have rockets. And here to give you a few more details, that's the Penny Darren that we start with. That's the first steam locomotive here that worked in England, actually. Here's the first production car, the Benz Velo, manufactured in Germany, by the way. And here's the Wright Flyer, constructed by the Wright brothers. This is how the speed records developed in the past 211 years until 2017. Here's Voyager 1, for example. Now the question of what a speed actually is becomes relevant here, because these are all speeds that we achieved on Earth, and these are heliocentric speeds now. The dashed line that you see here is an exponential growth law that has been proposed actually by Andrew Kennedy in the year 2006. And Kennedy proposed that this exponential growth law follows this kind of an equation here, and h in the exponent is the double time. And he proposed that the speed doubling time is about 100 years. That's what he estimated. And as per that little infographic here, we see it's actually closer to 15 years. If I just draw an exponential growth law here from the Penny-Darren to Voyager 1. So every 15 years, humanity doubles its speed records. And by the way, this corresponds to an annual growth rate of 4.7% compared to 1.4% that Andrew Kennedy estimated. And if we extend this, it's not shown in this plot. Of course, this goes up further and further here. It means we achieve 1% the speed of light within about 100 years from now. So this is, I would say, a natural extension of what we have observed in the past 200 years, that we are about to become an interstellar society in about a century from now, based on the data. Also, there's the 20% speed of light limit that we would achieve about in the year 2200, roughly speaking. So it's also not too far in the future. And by the way, there's no speed doubling beyond 50% the speed of light, if you have noticed. So, at least in my world of physics, we've seen other talks. But so I thought, why not extend this to special relativity? And though we don't need to go through each equation in very detail, here is the solution for what would collapse into an exponential growth law as per Kennedy et al. In the special relativistic framework. Okay, now let's assume there is a distant star. It's at a distance, let's say S, as we say Strecke in German. So it shows S. It's at a distance S. And let's assume at whatever top speed we currently have, be it 17 kilometers per second, like the Voyager 1 probe, let's assume that we have a current top speed that we call V0. Then the current travel time to that particular star would be tau 0, which is just the distance over the velocity that we currently have. So to Proxima Centauri, it would be 75,000 years. In the non-relativistic regime, then tau would be S over V. That's our future travel time, okay? Where V of t is simply what we've seen before. Just simply the exponential doubling law. Then if we, just for fun, divide tau 0, the time that we currently need, by the time that we would need in the future, and just insert this little equation here, turns out we can find an equation for the travel time in the future that we will need, assuming a doubling law of the speed. Now, depending on when we will actually launch our mission, this is the time that we will need to travel in the future, which depends on the time that we need to wait until then, our doubling time, and the time that we would currently need, plus the wait time, okay? That is, the longer we wait, the faster we will be. So the question is, when should we leave? Should we leave today? We're very slow. Maybe we should wait a few decades or 100 years, then we will be faster. So there is a danger that any mission that would go out to the stars would be overtaken by their successors. Well, so the question really is, when should we start? And Kennedy has called this the incentive trap of interstellar travel. And he computed this equation here for the non-relativistic regime. That's my little extension to high speeds. And here's a graph that I reproduced based on an example that Kennedy gave in his paper. Let's assume at some point we could reach Alpha Centauri at a distance of roughly 4.3 light years in 100 years. It will happen at some point in the future, be it in 100 years from now or 1,000 years from now. At some point we will have the technology to go to that stellar system within 100 years. Then the question is, should we wait another 10 years, 20 years, or 50 years until we are even faster, or when shall we leave? And the solution is at that point, we should still wait another 30 years, roughly speaking. Okay. And here's a little plot about the total time to the specific target, in this case, Proxima Centauri, Alpha Centauri system. From now, wherever now is, now here, meaning that at this point we would require 100 years. So this is the total time that it would take, the waiting time, until we reach that target. This is the travel time, it goes down because the speed increases, and this is the wait time, okay? And this solid black line here is just the sum of these two lines, and the red line is the relativistic correction. Phew, how do you feel? Still with me? Let's go. Wait 30 years. Faster. Question then is how to get there, of course. And I'm very interested in the possibility of using, as I said, light sails or solar sails to go there. So there are two candidate materials in the literature as of now. There is graphene for one thing, and there is aerographite. Graphene is a very transparent material. Its absorptivity is quite low, so it only absorbs 2.3% of the light that comes in. It has essentially no reflectivity, and the transmissivity is very high. So essentially is transparent. Okay. And that's why the radiative coupling is very low. Then there is aerographite, which has a very low volumetric density. And here are some numbers about the areal density. And what's interesting about this material is that its absorptivity is almost 100%. So that's why I say it's approximately. And it's completely black. No light comes in, and the reflectivity is essentially zero. So the radiative coupling is very high. This is what this material looks like. And here's just some glass, and you see it's jumping up and down because the electrons are bumping over back and forth, and so the charge changes. And this is actually a slow motion video, but I thought, why not bring a real sample? So here's actually a real aerographite sample. And if I would put it here, you wouldn't see it because it's black. How about a table here? And I will just leave it there for an hour maybe or two and see what happens. You're welcome to have a look when there's a coffee break or something. And I would be happy to have it back again at some point. Maybe to give you a closer look as to what it looks like. It's a very foamy material. This is not that particular sample, but another one. And it's been manufactured by my colleagues at the Technical University in Hamburg. That's the group that actually found that material, and they published it in 2012 in Material Sciences. So we go with this material now. But before we think about simulations of trajectories and about the physics, we need to talk about a few equations. How about this one? Let's think about the force that acts on a solar sail that is in space. It's a total force. It's a combination of the radiative force that is exerted by the photon pressure that comes in from the sun in this example, and it pushes the sail outward. There's also another contribution, that's the gravity. Here you see the sign. It's negative. Gravity pulls the sail back to the sun, and the photon pressure pushes it out. So the condition for any sail to become inbound, if we would put it into interplanetary space and neglect all the gravities from any of the planets, would simply mean that the total force acting on that sail would need to be larger than zero, which would mean it would be pushed out. Okay, we can find the solution to this by looking at what is in the brackets here, okay? This needs to be zero, the sum or the difference of these two terms. Okay, then we can divide by the surface or cross-section area of the sail on the left side. Also here on the right, then we have mass per surface area, which becomes our areal density sigma. So this expression here must be larger than zero. We can reformulate this into this expression here and find that it has units of kilogram per square meter. So this is kind of a critical surface area density of the solar system. It's kind of a material constant, if you will, of the solar system. So any material that fulfills this condition here it's lighter in terms of a surface area density, then this number, 10 to the minus 4 kilogram per square meter, will be blown out of the solar system. And as it happens, an aerographite layer with a thickness of 1 millimeter, so roughly corresponding to what we've over here, has a surface area of 1.8 times 10 to the minus 4, so roughly a quarter of that critical density. So if you would put this thing into space, actually it's 2 millimeters thick, so it's only half of what we need, but still, if you would put it into interplanetary space, actually wherever, doesn't depend on the radius or the distance to the star. Be it close to the star or very far away, it will just be blown out. So this is kind of an interstellar, it's not a probe, we couldn't probe anything, but it's an interstellar thing that humans have made that we could put up in space and would just be blown out. Of course, we should be able to attach some mass to it. So let's go and make some numerical calculations. So here's our basic equation again, and we did some numerical integrations. Where radius to the sun is a function of time, will that thing be after which time, which velocity will it have? And this depends, of course, on the force acting on the mass. This is the acceleration here. And the force we have over there. So we just need to plug it in and do some numerical integrations with the computer. So we start with a fictitious solar sail, and we assume a couple of different configurations. One is we have here, this epsilon refers to the thickness of our layer. So for one thing, we assume a very, very thin aerographite sail, 1 micrometer. Okay, and here's another one, we assume 0.5 millimeters. So still like a quarter of what I fear. This is actually what we've already been able to manufacture in the laboratory. So this we can produce. And then there's a couple of trajectories here. That's the radial distance from the sun as a function of time. That's logarithmic scale. So this would be a year roughly. Okay, and here we would be talking hours. And how about we start with this one? So 0.5 millimeters, and orange means we launch from 0.04 astronomical units. So assuming that we would have brought this very close to the sun, this is why it's down here, 0.04 astronomical units, and it would be blown out into interstellar space. Here the black line refers to the same sample, but launching from 1 astronomical unit. So initially, of course, it's further out, but the acceleration and the velocity gain is much lower. So in the end, this one will succeed. And here's the results for that very thin sample. Now, talking about velocities, it's also very interesting, of course, because usually we are used thinking about fractions of the speed of light. So here is what the final or the terminal speeds, let's say the escape speeds of these samples would look like. So you can reach a few percent the speed of light for the very, very, very thin sample here that would launch very close to the sun. Okay, and this is our nominal reference value here for starting at 1 AU, so out of the Earth's gravitational field, and with a relatively thick 0.5 millimeter sample. You would still achieve 0.01% the speed of light, which is actually quite fast. So all of this just assumes we have kind of a small hollow sphere maybe of that material and throw it out into space. Of course, we can extend this and add the gravitational field of the Earth here. So the force changes just slightly. The structure, of course, remains the same. In a 2020 paper, we simulated a fictitious release of one of these samples from the ISS. So we're thinking there's an astronaut and has a hollow sphere made of aerographite and just kicks it out of the ISS. What would happen? And depending on the actual payload that would be included, which would be of the order of a few grams, and of course, depending on the size of that soccer ball, that ball would have a certain trajectory. So these trajectories all refer to slightly different mass per surface area ratios. Also, we take into account the Earth's shadow. So whenever our simulated probe is in the shadow, there's no solar radiation, of course. It's just the gravity of the sun and the Earth that's acting. And all the green lines here those are the trajectories that leave the solar system. The black ones, they are inbound. They just fall back onto the Earth. And very recently, so that's not even yet published, my diploma, or I guess you would say master student of the Technical University of Dresden, Julius Kalab, he just completed his thesis with trajectories that even go to Mars and beyond. That's actually the paper that we submitted as kind of a proceeding to this conference here that I hope will be published in Acta Astronautica at some point. So Julius assumed various trajectories, or even from low Earth orbit and from geostationary Earth orbits, and aerographite-like sails. And it turns out you can reach Mars within, depending on the payload you have, with up to 1 kilogram in total mass. So that leaves you room for a few hundred grams of a payload if you have a large sail. You can reach Mars within a few weeks, 26 days. If you can aim sufficiently precisely. And second, the question still is how to decelerate, because at Mars currently we don't have another sun or another laser array. But the topic came actually up in the first day. John Moores, he mentioned that maybe atmospheric deceleration could be a thing. So that's something we haven't even looked at. But in the era of missions to Mars that actually include crewed missions, so when people will be there, I can well imagine that there will be instances where they cannot wait for 2 years, but they need, let's say, an electronic device or medicine on a very short time scale. So there will probably some need for fast delivery of small things, right? So this actually works for small things. Not talking about small very quick delivery of more humans or very heavy devices, but if there is something that you need very quickly and it can be light, then sails are actually an option if you can decelerate. Talking about deceleration, if we go beyond Mars, let's say to the Alpha Centauri system, for example, we would certainly arrive there with speeds that are a significant fraction of the speed of light. So when I heard about the Breakthrough Starshot initiative in 2016, I was really fascinated by the opportunity to go there in a human span's lifetime. But I was thinking, if we would invest decades of work in this kind of a project, then travel for another few decades, and then pass by in about 5 minutes or so, the efficiency is not actually very high. How about the possibility to decelerate, maybe get bound into in orbit? There is no laser array over there, but there is sunlight, or starlight, I should say. So can't we use the photon pressure of the target stars to decelerate? I'm going to show a little animation here. How about I start first and then press the stop button? So here's our inbound sail. It's not a sphere anymore. Well, in this particular publication, we assume it's a flat sail that can autonomously reorient itself. And what you see here on the right is the instantaneous g-forces, negative meaning it's currently being decelerated. Incoming velocity from infinity is 1,000 kilometers per second, just as an example. And this is Alpha Centauri A. Let's see what happens. The sail angle, by the way, the sail angle is optimized to maximize deceleration. And at some point, doing, it flips over to prevent being blown out from the system again. Okay, if it's perpendicular to the incoming radiation, then there is effectively no pressure anymore. You still see that there's still some deceleration acting. It's no photon pressure, but now it's just the gravity that tries to pull the sail back. It won't succeed though. This is outbound and will finally leave that system. But that's just an example, and I think it fits very nicely to the theme of this series here, in the light of other stars. Okay. We made a few calculations related to Alpha Centauri C, that is our most nearby star, Proxima Centauri, if you will. Turns out the illumination or the luminosity of that star is so low, it's a red dwarf star, that's very hard for an incoming sail to be decelerated to zero velocity unless you come in very slowly which means you would need to travel for thousands of years. So the whole idea is undermined, so to say. Luckily, Proxima Centauri is a member of a triple star system. So the idea we had is, why not go very fast to Alpha Centauri A, use photon pressure of that sun-like star, Alpha Centauri A, make kind of a gravity assist, which includes photons. So let's call it photogravitational assist to Alpha Centauri B, do the same thing, and then fly to Alpha Centauri C. So this seems to work actually. And I'll accelerate a little bit. How about I jump over this? And this is the projected speed history, so to say, of an inbound sail. It would come in very, very fast, then be decelerated to how much we can decelerate around that first star, be flung over to the next star, come in here, be decelerated again, and then finally be bound into an orbit. We had a follow-up paper where we actually found different trajectories, and can't go too much into the details here, but we were able to accelerate, so to say, and find the maximum speed that we can have that can be used to still decelerate an incoming graphene-like sail to be bound into captured into a bound orbit. And here's just an example for this. So the launch point is actually quite important, because at the point when we arrive in the Alpha Centauri system, the two stars, actually it's 3 stars, but the 2 most massive stars, they will be in a certain configuration. And they need to be in a very certain configuration because we cannot deflect by an arbitrary angle. So there will be a cone within which we have to deflect from the first star. So the second star needs to be within that cone for us to be able to go around the corner, so to say. In 100,000 years, it might be much better when Proxima Centauri is in the back. So for now, we are stuck with what it is. And here's just one example of such a trajectory. If we would launch in an optimal window in 2035, actually, this should be a 5-year, okay? Then this would be our escape velocity. The time to Alpha Centauri A would be 75 years. We would arrive on the 9th of September in 2092, at which point these stars align perfectly with our line of sight. There we go. Then it comes in. Now we speed down a little bit, and then it would only take, I think it's 6 days to reach that second star. And here we would be deflected using both gravity and the photons. And this will take another 46 years now. So that speed is actually realistic. The thing is, Alpha Centauri C is at, I think, 10,000 astronomical units, roughly speaking, from that inner binary. So that's why it still takes so long. And of course, if we have Alpha Centauri, we have more stars. So we extended this whole concept to all the other nearby stars. Well, at least 22,000 of them. In the paper, we show just the first 10 of an extended table that we published electronically. Here is the supposed travel times to these stars, given their actual astrophysical quantities, and that will dictate how much speed we can absorb upon arrival. Fun fact, we can actually use Sirius as an afterburner. We can use it the other way around. So fly first Sirius, that takes a few decades, and then use it because its luminosity is so high and accelerate even more throughout the galaxy. And even then, if we were able to move into a certain direction, we can use it as kind of a chain to accelerate through the whole galaxy and become faster and faster. And I should not stop without acknowledging my colleagues here, Rainer Adlung and Hubert Beisch, and also Boda Fiedler and Fabian Schmidt, who created that sample that I have here. And thanks to Michael Hipke, who helped me a lot with the trajectory simulations, and Julius Klapp at the THS, my student. Thank you very much.